Now coming to our next topic, that is magnetic field and magnetic field lines. So magnetic field is a vector that is defined by an influence over electric current or moving electric charges. As we know that magnetic field is produced by the electric current. Whenever there is a flow of electric current, magnetic field would be produced. Now how electric current is produced? Obviously by the movement of electric charges. Electric charges like electrons, protons, alpha particles, all these are electric charges. Movement of these electric charges causes electric current, and electric current causes the production of magnetic field. Now there comes the another concept, magnetic field lines. Magnetic field lines are imaginary lines that are used to represent magnetic field, and thus magnetic field lines help us to understand how magnetic field looks like at a given point and all the properties of magnetic field. So now we'll be moving to our question, that's why does a compass needle get deflected when brought near a bar magnet? So we have already seen that compass needle would get deflected whenever there is a magnetic field. So whenever a compass needle is brought near a bar magnet, there is a magnetic field near a bar magnet. So that is the reason why compass needle gets deflected. So I have drawn this diagram for you to see how the iron filings would arrange themselves around the bar magnet. So this is the pattern how it would look like. So in this case, the magnetic field direction goes from north to south outside the bar magnet. Remember, this word is important. Outside the bar magnet, the magnetic field line direction is from north to south. So this is the pattern in which the iron filings would arrange themselves around the magnetic field, and inside the bar magnet the direction of magnetic field is south to north, and outside it is north to south. Yes. So how do the iron filings arrange themselves? Because the iron filings experience a force outside the bar magnet, so they arrange themselves in the field of magnetic field. So why do they experience a force? Because of magnetic field. So obviously they will arrange themselves around the magnetic field lines. So that is what told in this paragraph. Yeah, even in this activity, we'll be seeing about the magnetic field lines and their direction. So I can skip this part, I guess, because we have already seen it over here in this diagram. So quickly moving ahead, magnetic field is a quantity that has both direction and magnitude. So magnetic field is a vector quantity. Will be as we know that a vector quantity is a quantity which has both magnitude and direction. So what do we call a magnetic field? It is a vector quantity. Give me some another example of vector quantity. So as we know, vector quantity is, there is one more vector quantity that we have studied in a 9th standard, that is velocity. How is velocity a vector quantity? Because it has both direction and magnitude. In the similar fashion, magnetic field is also vector quantity because it has both direction and the quantity that is its magnitude. Now moving ahead, direction of magnetic field is taken to be the direction in which a north pole of the compass needle moves inside it. So this is important. This is the by default direction of magnetic field that is to be considered. So by convention, the field lines emerge from north pole and merge at south pole, as we saw already. We can also say that magnetic field lines are closed curves. They are always closed curves, as we have already observed that they are closed curves. We have already seen that, right? They are closed curves. The relative strength of magnetic field is shown by degree of closeness of field lines. As we know, where the field will be stronger, there the magnetic field lines will be more crowded, because there the field would be stronger. Okay, all right. Over there the field lines would be crowded. Near the poles, magnetic field is stronger. That's why we see a lot of magnetic field lines over there and a crowded place, as we can see over here in this activity as well. See, over here this place is a lot more crowded because here the field is stronger. But here we can see less crowded, because as we go away from the magnetic bar, from there the magnetic field becomes a slightly less stronger. So that's why the field lines are less crowded. There is one more important point, that is no two field lines are found to cross each other. What is the reason that no two field lines can cross? Because if we draw a tangent at a magnetic field line, consider it is a field line and we drew a tangent over here. So by drawing a tangent over that point, we come to know the direction of magnetic field over there. See, at this point the tangent is drawn in this way, so the direction of magnetic field over here is in this direction, over here it is in this direction, and over here it would be something like this. So if two magnetic fields lines would be intersecting, so at that point their direction of magnetic field would be in two directions. That means when we will place a compass near that point, their compass should show two different directions. But that is not possible, right? So that's the reason why no two field lines can be crossing each other. Okay, now moving ahead, magnetic field due to a current carrying conductor. Now we would be seeing the magnetic field due to current carrying conductor. As we have already seen, a conductor is something that carries current. So something whenever we have an electric current, a magnetic field is produced. So now to know the direction of magnetic field and the movement of compass, this is an activity. In this activity, we will be seeing that whenever we have a circuit, a closed circuit, see we have a key over here because of which we will be closing the circuit. And in this diagram, we have it is told that in the circuit, whenever there is a electric current flowing and we place a compass over here, so there is a deflection in the compass. Over here, the deflection is towards east, and whenever we reverse the direction of current, the deflection of compass also reverses. It goes towards west. It means that with the reverse of direction of current, the deflection of compass also becomes reversed. Now, coming to this topic, magnetic field through a straight current carrying conductor, we would see that in this activity, they have taken a circuit in which they have taken a battery, an ammeter, a variable resistance, and also a copper wire to complete the circuit, a key, and also they have taken a cardboard which is placed perpendicular to our circuit. They have kept some compass over here, and they have also sprinkled some iron fillings over the cardboard. Now, they have told us that after the passage of current through our circuit, we would see that after some time, by tapping on the cardboard, the iron fillings would have arranged themselves in the concentric circles. Now, what do concentric circle mean? There is a circle, and then there is an outer circle, and then there is a more outer circle. There can be a number of concentric circles in this fashion. So this is the pattern in which iron fillings would be arranging themselves, and because of compass is placed over here, so we would observe a deflection in the compass. Now this compass, direction of the compass will give us the direction of magnetic field at that particular point. We'll be studying the how to find the direction of current, the direction of magnetic field, which is produced by straight current carrying conductor further. So before that, we'll be just seeing the mechanism of it. Now we can see that when we vary the current in the wire, the deflection on the needle also varies. This means that the deflection of the needle is somehow proportional, or we can say it is somehow dependent on the current carrying conductor. In fact, if the current is increased, deflection also increases. This means that current in the wire is directly proportional to magnetic field produced. It means magnetic field produced is directly proportional to current that passes through wire. So we can say it indicates the magnitude of the magnetic field produced at a given point increases as the current through the wire increases. Now, what happens to the deflection of the needle if compass is moved away from copper wire but current remains same? Now, if we keep it at a farther distance, the deflection decreases. This means near to the wire, the magnetic field is stronger. That's why the deflection is also stronger at the nearer point to the current carrying conductor. Now, come to the right hand thumb rule. So this is a rule by which we will be finding the direction of the magnetic field at a certain point due to current carrying conductor. So what this rule says? It says that imagine that you are holding a current carrying straight conductor in your right hand such that the thumb points towards the direction of current. So as we can see in this diagram, it is if we consider the current in the downward direction, and if we keep this current carrying conductor in our right hand, so what we need to do, we just need to curl our fingers towards the by keeping the thumb downwards, and the direction of curling of finger will give us the direction of magnetic field. So this is known as right hand thumb rule. Coming to this example, a current through a horizontal power line flows in east to west direction. They have said that there is a horizontal power line in which current is flowing from east to west direction. Now what is the direction of magnetic field at point directly below it and directly above it? Now because the current is flowing from east to west direction, as we can see over here, that north is towards upwards, south downwards, and east is towards right, and west is towards left. Now they have told that current is flowing from east to west, so direction of current is from right to left in this way. Now what will be the direction of magnetic field at point directly below it and at a point directly above it? Applying the right hand thumb rule, just keep your thumb from east to west. Keep it. Now you will see that your fingers can be curled in a certain manner. Now if we will see our fingers from the left hand side, means from west end, we will see they are curling in anti-clockwise direction. But when we will see our fingers curling from the east end, we will see they are curling in clockwise direction. So this is the answer that you need to write. Now coming to this these questions. These questions are also important for Cbse. Some students leave them because because they want to do a quick revision of the chapter, but these questions are really very important because after all Cbse paper is going to be Ncert based, so you need to do them. Now coming to our first question, draw magnetic field lines around a bar magnet. So this is what we have already studied earlier. This will be the solution of it. I have already taught you over here. Okay. List properties of magnetic field lines. We have also done this. So how to list properties of magnetic field lines? First, magnetic field lines are closed curves. Okay. Second, no two magnetic field lines can intersect each other. Third, where the magnetic field is stronger, over there magnetic field lines are crowded. This is your third point. You can write more points like we can say that relative strength of magnetic field is shown by degree of closeness of field lines. We can also write one more point like the direction of magnetic field lines outside the bar magnet is from north to south, and inside it is from south to north. There can be many points. You just need to write them. All right. Now coming to the next question, why don't two magnetic field lines intersect each other? I have already told you earlier in this video. You can just try to remember this, and if you don't know, watch this video again. Magnetic field due to a current through a circular loop. Now we have already seen the magnetic field through a straight current carrying conductor. Now we will be seeing the magnetic field due to a circular loop. We have so far observed the pattern of the magnetic field lines produced by current carrying straight conductor. Now we will be seeing through when a current carrying conductor is bent into a circular loop. We know that magnetic field produced by a current carrying straight wire depends inversely from the distance from it. I have already taught you this. So similarly, at every point in the current carrying circular loop, the concentric circles will become larger and larger. See, near the circular loop over here, at this point, magnetic field is in the form of concentric circles as it was in straight current carrying conductor. But as we move away from the circular wire in this way, these concentric circles become larger. Over here it will be in this way, and over here means they are just becoming larger and larger. And over here similarly downwards there is a concentric circle over here, and then they are becoming larger and larger, and at a point at the center this line will appear to become a straight line. Okay, now every point on the wire current carrying conductor, we will see it will give rise to magnetic field, which will be appearing as straight lines at the center of the loop, as I already told you over here. Now, as we know that magnetic field produced by a current carrying wire at a given point depends directly on the current passing through it. Therefore, if the current carrying circular coil has n turns, the field produced will become n times large. Why? Because if our coil is having n turns, then each coil will be producing its own magnetic field, and as the same coil is having n turns, so the magnetic field would be of the same quality, and so each magnetic field magnitude will be added up. So the magnetic field will become n times the original magnetic field. So we can write it n into B. Now coming to this activity, in this activity it is something same as we have already done it. So I am leaving it to you. Just do it on your own, and if you don't understand it, ping me in the comment section. I'll be explaining it to you again.